Okay, welcome everyone to the seminar. Today we have Maura Quezada from the University of Tokyo. So Maura is familiar to some of the audience members because she was the one of the PhD students of Celine Boehm back when she was at the IEEE in Durham. So Maura worked with Celine and Silvio Pascali on various aspects of CP violation and neutrinos. She's also worked with another former member of the CPPC, Sham, and now she's a postdoc at the University of Tokyo, and she's going to be telling us about some of her exciting work. So thank you for agreeing to give us a seminar, Maura, and why don't you go ahead?
Yeah, thanks for the kind invitation to give this seminar. Today I chose to talk about work that I made with in collaboration with Jelin Cho back in Durham, and Sham Balaji, who you say that was a PhD student in Sydney University, and it's basically based in these two works here. By the way, sometimes I get trouble with the screen sharing, so let me know if you cannot see the next slides. So now, I mean, basically what I want to discuss today is just the relationship or how we can use observations of circular polarization from photons to tell something about physics beyond the standard model, right? So the outline of the talk is just going to be a small introduction, motivation for the talk. And then I want to go into more detail about the relationship that exists between circular polarization and the CP asymmetry, what we call CP asymmetry, how they are related. And this is going to be in a very general way, in the sense that I won't introduce any kind of interaction yet. I'm just going to discuss the problem in a very, very generic way. And then I'm going to apply this formalism to the beyond standard scenarios. So in principle, I'm going to use two of them, a very simplistic one where I just introduce one sterile neutrino, and then I'm going to apply it to the minimal seesaw mechanism. And well, finally, the summary. So in the past few decades, we have collect a lot of knowledge about how the universe works. We have all this knowledge, or all this information collected in what we call the standard model of particle physics. And in this theory basically contains all fundamental particles and describes how the universe is made of quarks and leptons, and also how these particles interact among them and how they obtain their mass through the Higgs mechanism, except for the neutrinos, of course, in the frame of the standard model. However, this is still not a complete theory. There are still some questions that we need to answer, and then we need to look for answers in physics beyond the standard model. So this is something that we are working on in the present, trying to figure out what is beyond the standard model and how we can describe things that we still don't understand, or they don't fit in the frame of the standard model. And basically, I'm going to discuss a little bit of this kind of questions, but not all of them, of course, and very, very briefly. So, for example, we still don't know what is dark matter and dark energy. This doesn't fit in the standard model. We know that the universe is made, mostly made of something that is not ordinary matter. So we're trying to figure out which is this and how we can try to give them all the properties, trying to figure out everything about them. And the other question is where there is more matter than antimatter in the universe. So at some point in the universe, there must be something that happened that creates more matter over the antimatter. And one of the conditions to get this asymmetry is CP violation. However, the CP violation that we find in the standard model is not enough to explain this asymmetry. So we need physics beyond the standard model to understand and to explain this phenomenon. And The other question comes from neutrinos, where they get their mass. As I said before, in the standard model, neutrinos are not are massless. They don't get mass through the Higgs mechanism. So the question is, how can we include this, or why do they have mass in experiments? And there are some other much more questions that we need still to look for the answer, but we are looking for them, and they are still not answered yet. So based on the neutrino sector, as I said before, the standard model doesn't predict these their masses, but neutrino oscillation experiments, they have confirmed that these particles have a very tiny mass. It's a very tiny mass, and we could include these mass terms into the standard model by adding more neutrinos, right-handed neutrinos in this case, but we still don't know the nature of these neutrinos. For example, we still have some fundamental questions about the CP violation in this sector, if neutrinos are Dirac or Majorana particles, and if there are many additional species, how many of them could be 1, 2, or 3 more, or maybe n. We still don't know these fundamental questions. And most important, if we add these mass terms and then let the neutrinos obtain their mass in the same way as the other leptons, the next question we have is why, if they obtain their mass in the same way, in the same fashion, why neutrinos are much lighter than other leptons. So that is also another question that we need to figure out. And so far, one of the resolutions for this comes with the seesaw mechanism. So, which in this case, it predicts the minimal seesaw mechanism will predict two massive neutrinos, right-handed massive neutrinos. And the basic idea of this mechanism is that the acting neutrino masses is suppressed by these heavy neutrinos, heavy additional neutrinos. And if they exist, the radiative decays, they might be very significant, and then than those of the acting neutrino decay. So the decay width might increase, might be might be enhanced by these new particles with very large masses. And
Maura, I think the slides might have stalled. We're still looking at dark matter and dark energy.
So let me, maybe without camera, let's see if, yes.
There we go, okay.
Oh,
yeah, we've got
problems.
the...
Wait a second, yeah, I don't know how to solve this. But anyway, I don't know how to, yeah, sorry, I was here.
Okay, great.
Yeah. So can you see now, right?
Yeah.
All right. So this, I don't know, maybe it's okay if I just continue, right?
Yeah.
Yeah, okay. So if in this process we have standard model, sorry, how do I? Yeah, if in this process we have in the neutrino, heavy neutrino decays, we have CP violation, then in this process we can generate photons that might be circularly polarized, or they will be circularly polarized. And if there is CP violation in this process, then one process will create more of one kind of polarization than the other one, and then you will have a net circular polarization. You will be able to observe a net circular polarization. So that means that the circular polarization of photons can potentially provide a crucial way to measure CP violation in the neutrino sector of physics. So we can, by observing this net circular polarization, we can be also measuring the CP asymmetry in this kind of process. Now, this is very general way to relate to say this. So in the next one, I would like to, as I said before, I would like to explain a little bit how these two things are correlated. And I'm going to start by the polarized matrix element for the neutrino decay, where these are just the wave functions for final state and initial state and the photon polarization function. And this is the transition vertex function, which is parameterized with the electrical charge, magnetic dipole, electric dipole, and the anapole. Now, if we require that the neutrino is electrically neutral, so there's no charge, no charged neutrinos, we also require that the produced photon is on shell, and we choose the Lorentz gauge. This function vertex can be simplified and parameterized in terms of chiral components, left and right, where we have this definition here, which is basically defined in terms of the electromagnetic dipole moment of these neutrinos, right? So this is the simplification that we obtain by requiring these three things here. And we can compute the decay widths for the process of neutrino decay, where this matrix element is going to be related to the chiral components of the transition vertex function, this one. And by doing the same analogy for the antineutrino decay, we can also obtain the decay widths now, where now the matrix element is going to be related as well to the chiral component of this transition vertex function. And to give a small example of the relationship between CP asymmetry and circular polarization asymmetry, I have this example where I have a neutrino decaying, in the rest frame of reference with the spin plus 1/2, and this is happening in the z component, in the z direction. So the neutrino decay to another neutrino and a photon, the thing is that the angular momentum along the z-axis has to be conserved. So the only way that they can decay is that to a neutrino with minus 1/2 spin neutrino and a +1 photon, which is related to the positive polarized photon. And if we apply CP conjugation to this process, right, we will have an antineutrino, and then this antineutrino will have a minus 1/2. That because of conservation of the angular momentum along this z axis, then the photon will change polarization to a minus. So that is the relationship between these circular polarization photons to the CP asymmetry that we are looking for. And well, this is in general the definition, which is just the width of the neutrino decay process minus the width of its CP conjugate process. And the same we can explore the same in the case of a neutrino decaying into a photon that is negatively polarized, right? It's just the same. And the delta CP asymmetry for the process that does not depend on the polarization of photons is just the sum of these two quantities, this and this. And this is just the asymmetry between the two polarized photons. This will give us then the total number of these, of how much more you have from positive photons, or if you have less of positive polarized photons, for example. So this is the correlation between delta CP asymmetry and the photon polarization. So that's how the circular polarization can tell us about a little bit about how how we can actually measure or say something about CP violation or the CP asymmetry in this process by looking at these polarized photon signals. So that is the correlation. Now, if we explore a little bit more these factors still without saying anything about the model itself, but just saying that we have different loops I mean, we will have different loops in these decays. What we require is that when we parameterize these loops in this way, where this is just the factors or cofactors that comes in these loops, and this is purely the coming from the loop integrals. So we see that we require an imaginary part, and this imaginary part, it will only appear if the mass of the initial neutrino is larger than the mass that participate in the loop that induce the decay of this, the relative decays of these neutrinos. So this is very important, because if this is not the case, then no CP violation can be generated in these processes. Now, the same thing we can do for Majorana neutrinos. So far, I've just been describing what is for the case of Dirac neutrinos. But for the case of Majorana neutrinos, we can basically follow the same steps. And the difference will come from the fact that for Majorana neutrinos, we have to take into account for the total matrix element, the antineutrino decay as well, right? Because Majorana is its own antiparticle, so we would just need to include this. And the matrix element is just exactly the same as I showed before for the two different cases. So now the delta CP plus and minus will be only the difference between the decay widths of the case where we generate circularly polarized, positive polarized photons and negative polarized photons. So it's a slightly different, but still we just follow the same steps as before to obtain the form of this delta CP, right? Now I will go into the simplified case where I introduce a sterile neutrino to only one sterile neutrino to this case, and this is going to be just to show how we obtain this delta CP in a more clear way. So first, I'm gonna discuss a little bit the case of standard model contribution. And what I mean by standard model contribution is just the sterile neutrino induced and the decay, relative decay induced by standard model particles. So in this case, in the loop, I will have W bosons and leptons. And in this case, the mass of the sterile neutrino is smaller than the W boson, right? So in this scenario, this is the form of the transition form factor, transition vertex that we have here, where we can identify here as the right chiral component of the transition vertex and the left component. And in this limit, and also in the limit what the in the limit of the sterile mass being smaller than the boson, W boson mass, this is always real. This function here, which is it's a very well-known result from literature, is going to be always 0. So there is no CP violation coming from these diagrams, right? So in this case, in this scenario, there's no way that we can generate this CP violation in these relative decays. Now, in order to enhance this, in order to create, or in order to see if we can observe some CP violation coming from these decays, we need physics beyond the standard model. So in this work, what we did was introduce two new particles, a fermion and a scalar, that were with opposite charge. And this is the Lagrangian, that the interaction describe this, the coupling between these new particles and neutrinos, sterile neutrino and active neutrinos. Now, if we introduce these new particles to the model, then we have now an extra term in the total matrix element, and then the chiral components of the transition, the vertex function, transition vertex function, will have, again, the standard model contribution that I explained before, and we have the new contribution from the loops of with the new particles, the new physics, these loops. And the delta CP, let's say for the case of negative circularly polarized photons, production of these negative circularly polarized photons, is going to be given in terms of again, it has the same form, but now we have combinations of the standard model contribution and new physics contribution. And as I said before, this term is going to be always real and positive. So the only thing we have to care about is this imaginary part. We have to compute this imaginary part now. So this is just going to be given like this. And again, this is coming just from the loop integrals. So we have to perform the loop integrals. And in the same way, we can define delta CP for plus, for positive circularly polarized photons. Again, it's going to be of the same form. And in the case, I mean, as I said before, to get an imaginary part different from 0, now we have to require that the mass of the sterile neutrino is larger than the mass of the the addition of the 2 new particles in the model. So this is the thing that we have to require in this calculation. And well, the only thing that is left to do is the loop calculation. We have to compute these loops. And of course, I'm not going to go into details of how to compute the loops. But in general, the form that we obtain in these loops integrals is a function. I mean, this is after integrating over Feynman parameters. And then we obtain a function and usually a logarithmic function as well. This will depend on the masses of the new particles and the last Feynman parameter here. And I mean, this corresponds to loop 1, loop 2, of course, and left and right-hander components. And in the case of the left component, this is proportional to the mass of the active neutrinos. So if we take the limit to 0 of these masses, then there is no contribution from this, right? This is going to be 0 or extremely suppressed. Now, to factorize or to take out the imaginary part of this object here, what we require is that the argument of this log function has to be negative. In these cases, when we will obtain this negative, this imaginary part. So this is what we call CP violating condition in our work. So we require this, and this happens within these 2 values here, y1 and y2, which these are basically found when this is equally to 0. We solve the system and then we find these 2 quantities here, which are within these 2. I mean, these 2 are obviously larger than 0, but they are smaller than 1. So this is very important because this is where all this calculation relies on in this part, right? We need to do this. And finally, if we compute the integral of this object here within these 2 new integral limits, we obtain the complete form of delta CP for the case of negative circularly polarized photon, where this is just the result of the full expression of this. And as I said before, for delta CP plus, which is proportional to the mass of the active neutrino square, this is strongly suppressed. So there's not much contribution from this case. So this is, as I say, I just want to emphasize that this is the important part of the calculation. So this is what we've been calling the CP violating condition in order to obtain these imaginary parts from these loop calculations. Now we can do the same, and now for the heavy neutrino decay for the minimal seesaw mechanism. So if we do this, we go back to the standard model scenario. We go back to the case where the neutrino decay, radiative decay is induced by standard model particles. However, in this case, the two neutrinos that we add, the two heavy neutrinos added in this model, are going to be heavier than the W boson. So in that case, we will be able to generate an imaginary component in loops decays, and then that means that we will be able to see some CP asymmetry. So this is just the Lagrangian for this type of interactions, where here, this is just a fraction of these new particles in the neutrino mixing matrix. And to compute this numerically, we have used Quezada parametrization, which is basically parameterized in terms of this omega phase, we call Quezada phase. This is a complex phase, and we will just compute again the loops for all the channels for this radiative neutrino decay, and in general the vertex transition function is given in this way, where this pi just corresponds to the computation of each loop in this figure here. And again, to get non-zero imaginary part, we will require that the mass of the initial neutrino is larger than the mass of the W boson plus the mass of the leptons. So in this case, we are just ready to compute these quantities here. And if we follow all the steps that I described at the beginning of the talk, we can arrive for the case of Dirac neutrinos for a more specific expression for this delta CP plus minus, where now these are given in terms of this parametrization, which is the Jarscough parametrization, imaginary part and real part. And these functions here are just all loop function contributions. It's just the addition of all 6 functions after being integrated, and also after requiring this CP violating condition that I said before. So this is just the final result. And for the case of Majorana neutrinos, we can also follow again the previous computation at the beginning of the talk, and parameterize as well in terms of the Jarscough parametrization. And in this case, we have this new definition here, which only appears in the case of Majorana neutrinos. So, and again, these functions here are just a full computation of all the addition of all loops computations. And in this scenario, we have 3 channels of interest. One would be active neutrino decaying into active neutrino plus a photon, which as I said before, because this neutrino mass is smaller than the W boson mass, then there is no CP asymmetry. It cannot be generated in this case. Now, we have also compute the heavy neutrino decay into active neutrino plus photon, and we have compute the CP asymmetry numerically, but this is very tiny, so it's very, very small. So it will be very difficult to observe this kind of signals. And the other channel that we have is the heaviest of the neutrinos, the right-handed neutrinos decaying into the lighter right-handed neutrino plus a photon. So if we have done this for different benchmarks. So here we have the delta CP. This is the total delta CP for the case of heaviest neutrino decaying into a lighter right-handed neutrino for different benchmarks. And in this case, we have used the best fit oscillation data to compute this, and we have set no Majorana type CP violation. So the only sources of CP violation here will be coming from the loop calculation itself, the loop itself, and the delta CP violation phase from the lepton mixing, because as well the Casas-Ibarra phase is also set as to be real. So there are just only two sources of CP violation in this one, and we see that the delta CP, the asymmetry is quite large, can be quite large, 10 to the minus 3, 10 to the minus 2, but the branch shield ratio is very, very small, of the order of 10 to the minus 17. So it would be very difficult to observe this process here. We have also set again the same situation as before, but now instead of a real Casas-Ibarra phase, we have set this to get an imaginary component. So there is an additional source of CP violation in this case, and we can see that the delta CP is still quite large, and also the branch shield ratio could reach up to 10 to the minus 11, 10 to the minus 10 in these cases for the different range for the different benchmarks of these neutrino masses. So finally, we made a scan of these quantities delta CP and also the branch shield ratio, and the blue scan, the blue points here, the blue data corresponds to the case where we have used only a phase set to be real, so the real case, and the red dots here corresponds to the case where we include an imaginary component to the Casas-Ibarra phase that goes from -5 to 5. And in the case of when we add this imaginary component to this Casas-Ibarra phase, we have that we can reach up to even 1 in the delta CP. However, the branch shield ratio is still very, very small, 10 to the minus 10, minus 12, and between 10 to the minus 12 and 10 to the minus 10. So this is still very difficult to observe. Now, but I mean, delta CP will be very, very large in that case. So yeah, I mean, now just a summary. I mean, in this, I discussed a little bit about how secret polarization of photons can provide or might be a way to measure CP violation in relative neutrino decays. And this is because in this process, if CP is violated, then we might have an asymmetry between these two kind of polarized photons. There is a correlation between the CP asymmetry and the photon polarization, which is the one I discussed in the second part of the talk. And I show how these two are connected and how these are related. And then we also discussed using a very simplified scenario how to obtain the non-zero imaginary part, right? So there is where I introduce what I call the CP violating condition here. Then we apply this formalism to a minimal seesaw model where we have introduced two heavy neutrinos, 1 and 2. And then we found out that the CP asymmetry in these cases is very small. It's of the order of 10 to the minus 17. Maximally, actually, this is the maximum we could reach in this process. And yeah, in the case of the heaviest neutrino, right-handed neutrino decaying into the lighter right-handed neutrino channel, CP is significantly enhanced. So we can obtain from 10 to the minus 5 to 10 to the minus 3 with a, I mean, branch shield ratio that is still very small, but is of the order of 10 to the minus 10. And well, the problem with this is that there are a lot of limitations in how we experimentally measure this polarization, how we measure the polarization of high energy photons coming from space, for example, because technology still doesn't exist. So yeah, that's all from my side. Thank you.